Another type of collision that we're going to be looking at is called a reverse inelastic collision. So it's similar to an inelastic collision except it happens in reverse. That's where two objects are initially stuck together moving as one object, and then they separate and move with their own separate velocities. This type of collision is also sometimes called an explosion. Okay, so momentum is still conserved as long as the system is isolated. So here's my conservation of momentum statement. Now in this case, it's kind of like initially you have things that are acting like one single object and later they act like separate objects. So here's kind of how this looks like the reverse, you can see, of an inelastic collision. So initially these two masses are acting like one mass moving with the same velocity, and then they separate and have different velocities in the end after the explosion. Here is a hilarious correction the New York Times made in 1969. So press pause. It really is worth your time just because it's really an interesting historical thing that happened. Press pause, read through this, and then I'll kind of give you some more background. Okay, so this is, like it says, it's a correction published in the New York Times. And I guess what happened was in 1920, the New York Times took it upon themselves to call out a famous scientist, Robert Goddard, and claim that he was stupid for thinking that rockets could ever move through space. Okay, and the New York Times says, "Oh, silly Professor Goddard, don't you know that according to Newton's third law, the only way to propel yourself forward is that you have to push backwards on something in order for that thing to push you forwards. Just like, you know, how when you go swimming, your hand pushes back on the water and the water pushes your body forwards." And so they said that Professor Goddard was an idiot for proposing that a rocket could move through space, because in space there's no matter, there's nothing to push on, so you can't propel yourself forward. This was in 1920. They insulted him, even they put his title chair in quotation marks. So that was a long time ago, 1920. Now, 49 years later, they decide to print a correction, and the correction they print says further investigation have confirmed the findings of Isaac Newton. Okay, and what they're talking about here is they're saying that rockets can move through a vacuum, not because they're pushing on something, but because of the conservation of momentum. So the way a rocket is propelled in a vacuum, you can imagine it as an explosion. So you initially have a rocket with rocket fuel. Okay, that's moving as one system, one object. And then the rocket pushes the fuel out the back very fast. And then as a result, to conserve momentum, the rocket itself gets pushed forwards. So that is a way to propel something even in the vacuum of space. And the New York Times admits that they were wrong to make fun of Professor Goddard in 1920. They published this 1969, July 17th, the day after a rocket landed on the moon. Okay, so it's just a funny little historical correction. I don't know, I think it's really funny. And it has to do with conservation of momentum here. So let's go through an example of a reverse inelastic collision, also called an explosion. And let's try to calculate the recoil velocity for a handgun using these values that are given to you here. Okay, so press pause, take some time, see if you can set it up correctly and work through it, and then press play to go through it with me. So my events are going to be before the explosion and after the explosion. I'm going to look at the total momentum of the system before the explosion and the total momentum of the system after the explosion, and that's going to help me figure out the velocity that a gun would recoil with when you shoot it, when you shoot the bullet. So initially, my gun and my bullet are acting as one object, and initially they're at rest. Okay, that initial velocity of both the gun and the bullet is 0. So my total initial momentum is 0. That means that after my explosion, the momentum has to remain 0. And so first I'm looking at the momentum of the bullet after the explosion. That's going to be equal to the mass of the bullet times the velocity of the bullet after the explosion. And I'm using the mass of the bullet here and this muzzle velocity. That's the velocity the bullet leaves the barrel of the gun. So I find that after the explosion, the bullet has 2.8 kilogram meters per second of momentum. And so I know that the gun will also have a momentum because I know the total momentum has to be conserved. So the momentum of the gun afterwards is going to be equal to the mass of the gun times the velocity of the gun after the explosion. and there I've plugged in for the mass of the gun. So now I can look at my total final momentum. It's just the sum of those two, and I get this mathematical expression. I know that this thing here, though, has to add up to 0 because momentum is conserved. And I find that the gun comes away with a velocity of 2.33 meters per second. It's negative because it's in the opposite direction of this velocity, and I said this one was positive, so this one ends up having to be negative. So this is actually a huge issue when you're dealing with shooting, especially heavy projectiles like what's being shot here. So this is a very, very massive projectile, and it's being shot at a very high speed. So what happens here is you have tons of momentum going off in this direction. And that means to conserve momentum, this howitzer, whatever this is, rocket launcher, is going to be propelled backwards with a huge velocity. So there are a couple mechanisms that need to be put in place to prevent, this from just shooting backwards and hitting everyone. One of them, if you notice how there's a bunch of gas shooting out here. And that gas looks like it's coming straight out to the sides, but it's actually coming a little bit out to the backwards like this. And that can, even though it's gas or dust particles that are very light, you can have those come out at really, really high velocities, so they can carry a lot of momentum with them backwards to balance out that momentum up there forwards. Also, if you've ever seen one of these guns in action, this barrel part here is kind of it's on like a pivot. So when this projectile is shot forward, this huge, massive barrel is allowed to pivot backwards while the rest of the gun kind of remains stationary. This huge, massive thing here pivots all the way back, and that takes a lot of momentum with it too. Even just a small handgun here has these vents on the side. These vents are kind of blowing, would allow air to escape backwards, kind of back like this in that backwards direction. That can also lessen the recoil velocity of the gun by taking some of that momentum, that backwards momentum that would be absorbed all the way by the gun. It can kind of come out with those vents.